For our chemistry project, we built an arc furnace powered by a welder to learn about melting metal. First, we started by preparing the insulated firebreak itself with help from a friend. Once we had the furnace ready, we powered up the welder to arc and heat up the metal. Unfortunately though, instead of getting a consistent arc, the stick and nail just welded together, preventing any further reaction. After a bit more testing, we found a way to get the electricity to arc without welding together. The angle to hold it at though was really precise and difficult, as you can see here, so we couldn't get it consistently. We tried many different setups, but none of them seemed to work well enough. It would always go out before we could get any melted metal. Our friend, who was there to help with the welder, as we didn't really know how to use it, got a big steel screw that was big enough to not weld together immediately. We put some copper couplings in the furnace after weighing it, and it started without errors. We ended up with this great result.
As you just saw, we heated 2 solid pieces of copper to its melting point in only a small amount of time. But how much energy does that actually take? Using the delta E equation, or enthalpy, we can find out. The enthalpy equation is fairly simple. To calculate the joules of the energy over time, we need to find the specific heat of copper. Specific heat, or heat capacity, is how many joules it takes to heat 1 gram of a substance by 1 degree Kelvin. The specific heat of copper is 0.385 joules per gram. Next, we need to find the weight of our sample, which is about 24 grams. Then all we need to do is find the change in energy over time. Assuming the copper started around room temperature, or 298 Kelvin, and we heated the sample to copper's melting point of 1,358 degrees Kelvin, that is the temperature change of 1,060 degrees Kelvin. Multiplying all these numbers together, the amount of energy that was transferred into the copper to bring it to its melting point was 9,794 joules. That's a lot of energy.
However, we aren't quite done. There's more energy change to observe after the melting point. Let's find the enthalpy change of the melting copper. For this, first step is the molar enthalpy of fusion per mole, or delta H fusion. This is an understood 13,050 joules per mole, approximated to 13,100. This has been determined by experts and is a trusted source. It takes 13,100 joules to melt copper at its melting point of 1,058 degrees Kelvin, our next step is finding the molar mass of our sample, which is 24 grams. Given the molar mass of copper, we can take 24 divided by 63.55 grams to get 0.377 moles. Lastly, we multiply these two values to get our delta H, which is 13,100 times 0.377, making 4,950 joules change of enthalpy. This only observes the energy after the melting point, so we need to add the energy before, found in our last demonstration. So to add these two up, we get an answer of 14,744.4 joules.